Now, once this is done, what is followed in a particular in a transformer architecture is to what is called as the causal attention. So let us look at what is masked attention or causal attention. Also called as the causal masking or causal attention. So recall that in an autoregressive model, xt depends on x1 through xt minus 1. So which is, the dependency is a causal dependency, right? It only every tth token depends on x1 through xt minus 1. It does not depend on future, right? But the way the attention mechanism has been defined here is that if you look at the way the attention weights are computed, the attention weights are computed by assuming that each of the token depends on every other token in the sequence. So which means that we are not considering the fact that in an autoregressive model, every token depends only on its past, but it does not depend on the future. But the way this attention this attention is computed, we are making an assumption that every token depends on every other token irrespective of its position in the sequence, right? So to ensure that the attention mechanism that we have defined adheres to the autoregressive nature, so we'll have to ensure that we modify depends on this, and therefore to ensure that xt depends only on the past and not on the future, depends on the previous tokens, and not on the future tokens. The attention mechanism has to be modified. Okay, to ensure that the model that we are building is truly autoregressive. How is it done? This is done by using what is called as a masking mechanism. So define a mask matrix denoted by M. So that M is in T cross T space. Now, the ijth element of this M is 0 if j is less than I, and it's equal to a very large value. Mathematically defined it to be minus infinity if j is greater than I. Okay. Now what you do is that modify the attention weights as follows. So now with M, the attention weights are modified as follows. Modify the attention weights as follows. So now define A with the masked attention as softmax of, remember it was previously qk transpose divided by root of dk. This is what we had earlier. all you need to do is add this M matrix element wise to this particular matrix and then take the softmax. Now remember that this addition is possible because we are doing an element wise addition. So let's say that this addition is a matrix element wise matrix addition. Why? Recall that both of these matrices, right, Q, K transpose, it's a T by T matrix. So we just saw this, right? A, the attention weight, is a T by T matrix, and so is the M matrix. So M is also a T by T matrix. So both of these can be added element wise. Now, if you look at the definition of M, so what is it actually doing? Is that whenever we are looking at the past, okay, it's doing nothing. So it is just retaining Q K transpose. That's doing nothing. So because it's 0. But whenever we are looking at the future, wherever your J is greater than I, what it does is that this will add a large negative number to Q K transpose, whatever we have gotten. So now remember that softmax has an exponential operation here. E power some scalar is what softmax does. Now, if this scalar is a very large value, so that would be put to 0. Right? So the weight corresponding to any future token will be put down to 0 because the value that arises before softmax because of the presence of M will be very large, right? So this will ensure, so this AM, or rather the element in AM corresponding to a future token, to all the future tokens, in fact, to the future tokens are put to 0 via addition of M. So once we add this mask matrix via the M addition, right? So this is the trick that is played to ensure that the model that we build will be autoregressive in nature. Okay. So once we get this AM, so we will use this same AM to multiply with the value matrix. And once we multiply it with the value matrix, we get another representation of the data. And this representation will be such that the dependence of every token is only on its past, but they don't depend on the future. Okay, so this is the idea of causal masking or causal attention, which is used in all the decoder only generative models which are based on attention mechanism. Okay, so one other trick or the technique that is used in a transformer based autoregressive model is what is called as a multi-head attention. Multi-head attention. Okay, so just recall that what did we just say? Attention mechanism takes the data vector that lies in dm dimensional space and projects it onto dv dimensional space, right? So here in the discussion so far, we did this projection in one shot, which means that all the m dimensions of data were transformed using one triplet of the query key and value matrices. There's no need why one should do it that way. In a multi-head attention mechanism scenario, what is done is to ensure that the expressibility of the model is increased. So if you do it in a single projection, in a single step projection, then the expressibility of the model may not be large. So what is that? What do I mean by that? So what we are actually learning are these three matrices, right? The weight matrix, the query matrix, key matrix and the value matrix. There are only three matrices that we are learning. So instead of only learning three of them, what if we divide the data dimensionality DM into multiple subparts and learn a query, key, and a value matrix corresponding to each of the subpart or subdivision of the data dimensions, and learn as many attention mechanisms or as many attention vectors corresponding to each of the subpart of the data dimensions and combine them up. So this is the basic idea. This will increase, this is believed to increase the expressivity of the architecture that we are looking at. So that is the idea. So what happens is, define h, okay, which is a scalar, positive real number, as the number of heads. Number of attention heads. So these are called attention heads. Okay. So what is done is, so D typically, dk is made to be equal to dm divided by h. Okay. Now what is done is, the dimensionality of the query and the key matrices are made to be equal to dm by h. So what is actually being done is, now if there are, if the desired model dimension is, let's say, 512, and you want 8 attention heads. So what is done is, you learn a query, key, and value for each of the subdimensions of 512 by 8. Okay, so that's the idea. So typically dk is made to be equal to dm by h. So now you divide dm into parts of h number of parts. Okay, so before you learn the attention for each of them separately. So what is done is, for each h heads, so now each of these is called an attention head. So for each of the h heads, do the following. So define a query matrix. Let's call it qi or qj is, so x times w jq. Now this lies in r t comma dk. So note that my dk now is dm by h. Okay, what I am doing is learning the query, key, and value matrices for each of the heads separately. So kj is x times w jk, and this lies in r t comma dk, same as that of query vector, and v j is x w j v, which is in r t comma dv. Okay, now what I do is I compute the attention per head. So this compute the attention per every head as the following. So we have attention qj, kj, and vj. So this is the attention that I have computed for the jth head. So what did we call it? I think it was this was that, and we called attention as z. Okay, so let's call this as z. So this is the attention matrix corresponding to the jth head now. So now this belongs to r t comma dk dv space, right? So this is in r t comma dv space. Now what is done is, after, in the end, all the individual heads are concatenated. So all the individual attention heads are concatenated this way. So let's call that as Z concatenated, as you take Z1 concatenated with Z2, concatenated with Z3, and so on, and we have finally ZH. So all the attention matrices that are gotten by the individual heads are concatenated. So this lies in R T times T cross. Each of them lies in dimension dV, and we have h of them. So this is dV times h. Now recall that dV times h, so this is also made to be equal to dV typically. So now dV times h gives us dm back, right? So that is the desired model dimensionality. This is also equal to this is equal to R T cross dm. So we get back T cross dm by doing this. So finally what is done is the following. So once it is done, you define the multi-head attention over the x. Remember that we are operating on x as ZC times another matrix WC, okay, which makes it in R T cross dm again, right? So now where WC is in R dV times h cross dm dimensions. Now note that, while I just said that this is typically made to be equal to dV, in general this need not be the case. dV can be different from dk. In that case, just to ensure that we put back data in the dimensionality of dm, okay, we will ensure that we project the concatenated multi-head attention onto one other space WC, where WC will make sure that all the attention heads are appropriately combined to get us back to dimensionality dm. So now here all the QJ, or rather let's call them as WJQs, which are the query matrices for each of the head, and we have WJK, WJV, and the final matrix that would combine all of these into these are learned for J equal to 1 through 1 to up to H. So in multi-head attention, what we do is, instead of learning one query and the value matrices, we learn H of them, okay, each corresponding to a head. So this is the idea of multi-head attention. So note that multi-head attention also does the same thing, right? I mean, it starts from X, that is in R T cross dm, and this will project it onto Z, right? That is again in R T cross dm. We are doing the same thing as in the case of a single head attention, but instead of doing it using one query key value matrices, we split the data dimension into H subparts, and for each of the subpart you learn the attention separately and concatenate them all using another projection matrix called WC. So this is the idea of multi-head attention, okay. So now again, we are back to where we started from. So what we have right now is a representation Z of the given input data X, right? So remember that we still have to ensure that what we are doing is modeling p theta, which is the autoregressive model. Okay, so let's do that. So now we have obtained a z, okay, that lies in R t cross dm space, okay, which is a representation, which is a data representation, let's call it, which is a representation of data given by the multi-head attention. Given by the multi-head attention, right? We'll have to work on that now. In a transformer-based architecture, once the multi-head attention is computed on the input impedance, they are followed by fully connected layers. This is applied to ensure that the whole architecture has more expressibility compared to only having multi-head attentions. But if you observe the entire attention mechanism, the multi-head attention mechanism, are predominantly the linear operations because they are all matrix multiplications. So every matrix multiplication is a linear operation. Therefore, if one needs to represent a nonlinear function, which often is the case with input-output relations in tasks like natural language processing and so on, only linear transformations would not suffice. Therefore, attention layers or multi-head attention layers are followed by fully connected layers, which are multi-layer perceptrons, fully connected neural networks, that would impose a lot of nonlinearity and therefore expressivity on the entire architecture. So we also have this classical result from neural network theory that a single hidden layer neural network is a universal function approximator, in that you can approximate any arbitrary function to any closeness given that you have enough number of neurons in the hidden layer. Having a fully connected neural network after multi-head attention would serve the purpose of making the entire architecture more flexible. So therefore, once the multi-head attentions layers are applied, so you have a fully connected layer or sometimes there can be multiple fully connected layers as well. So that's mostly a design choice, and it's a typical fully connected layer. How do we do it? And one other thing to be noted is that these fully connected layers are applied separately for each of the token. So we have here, once there is an attention layer applied, we have Z, which is a representation of the input tokens, and all of them are in dm dimensions, and there are t of them, right? Because capital T is the number of tokens that we have in the input. Now these fully connected layers are applied on each of the tokens separately. So just to contrast this with the attention layer, while computing the attention layer, the attention for a given token is computed by considering the influence of all the other tokens that are there in the sequence. Whereas in a fully connected layer, each of the token is treated separately, and fully connected layers are applied on the embeddings of each of the individual tokens separately. Okay, so how do we do that? For each of the position j in the sequence. Let's call this let xj be the jth token. We have the jth token, and instead of calling it xj, let us call it zj, because we have already transformed that in the space represented by the attention mechanism. So here zj sits in r dm, right? That's the transformation that we have done. So fully connected network or layer, let's call this FCL for fully connected layer, that is operating on zj is defined as some nonlinearity, let's call it sigma. We have zj times w1 plus some bias b1 and multiply that with some w2 and you add b2. So this is one example of how one would apply a fully connected layer. So this is a single hidden layer neural network where C is a nonlinearity. Example can be typical activation functions such as ReLU or sigmoid or tanh or any one of them. These are examples, and W1 and W2 are again learnable parameters. These are learnable parameters. So in this particular example, W1 is in RDM cross, let's call it some DF, and W2 is in RDF cross DM. So once this is done, right, see the output of this fully connected layer call it z cap j. This will be in the same dimension as that of z, right? Because we have adjusted our w1 and w2 that way that they will be in the same dimension as that of z, that would be dm. So there will be t tokens, all of them in dm dimensions, right? So now what happened sequentially? So first we started with an input vector, and then we learned an embedding starting from random initialization. Then a multi-head attention is applied, so we get some representation z in some dimensions dm. That is followed by fully connected layers that are applied individually to each of separately to each of the tokens, individual tokens, right? Okay, so then once this is done, we have some representation z cap j in dm dimensions. So what is to be done next is that we'll define the final output layer. Now let's call this as z tilde. I've been using too many notation. Z tilde at jth location to be equal to some. So we have zj cap, which is the representation that we are getting from the output of the hidden layer, the fully connected layer. We have some other matrix, let's call this as wp plus some bias bp, and this is in rv, where v is the vocabulary size. So what is happening here is that the zj cap, which is the which is the output of the fully connected layer, is projected onto the space of vocabularies via a linear projection. Linear projection, that is WP. Now, what is the dimensionality of WP here? The matrix WP should be in RDM, because that's the input that it gets, and it will project to the space of V. Okay. Now what is being done is that you just have a linear projection onto a real space that would have the dimension equal to the length of vocabulary. Okay. Why is this important? Once this is done, remember what we need finally is a distribution over vocabularies. So vocabulary is a discrete set of possible tokens. What we need is a discrete distribution over all the tokens in the vocabulary. Right now what we have, the zj tilde that we have, is a v dimensional real vector. Now we need to translate that v dimensional real vector into a distribution over the vocabulary. So how do we do that? We have the usual trick, which is our softmax. How do we do that? So y cap j, which is the final output of the transformer, is given by softmax over zj tilde, and this is what we have as the output of the transformer at the jth. This is the final output of the transformer, which will give us a distribution over all possible tokens at each of the jth sequence. So not every if you have capital T as the input, the length of the input tokens, then the output of the transformer would give you a distribution over the vocabulary by via the softmax operation over the representations that we have gotten at the output of the fully connected layers. This way we get a discrete distribution over the vocabulary at each of the tokens of the input sequence.